Hello and welcome to our webinar. Our topic today is Wall Bracing 5, Wall Bracing Examples in High Seismic Design Categories D0 through D2 regions. This is part 5 of our Wall Bracing series. If you haven't watched parts 1 through 4, please check these out. They are available on our website for free on-demand viewing. Today's session will put modules 1 through 4 into practice as we work through examples of wall bracing design using the 2018 International Residential Code. My name is Karen Beebe. I'm the Western Region Manager for APA's Field Services Division, and I will serve as moderator for today's session. APA is a nonprofit trade association representing manufacturers of a variety of common structural engineered wood products. In addition to quality verification and product testing, APA conducts research to improve engineered wood products and the systems where they are used. We also educate users and specifiers on the product's intended use and potential applications. Before we start today's webinar, I need to cover some housekeeping details. The presentation will last about 80 minutes. Handouts of the slides can be found in the control panel on your screen. I'd also like to note that today's webinar is approved for AIA and ICC continuing education credits. After the conclusion of the session, you get your customized certificate of completion. Your feedback is important to us. Please note the QR code on your screen. If you have a smartphone handy, you can open the camera app, point it at that QR code, and it'll take you to our survey for today. Today, we have two speakers, Alita Dean and Larry Owning, who are both engineered wood specialists with the Field Services Division of APA. In their role, they work with designers, building officials, and builders on the various engineered wood products that are used in buildings today, and they consult on engineered wood use in construction applications. A few notes on their backgrounds. I'll begin with our first speaker, Alita Dean, professional engineer. She is based in California and she supports the Southwest, including California, Arizona, and Nevada. Prior to joining APA, Alita worked as a structural engineer for 9 years, designing a variety of building types, including schools, commercial construction, and residential. Alita is a licensed professional engineer in the state of California, and she has a Bachelor's of Science in Architectural Engineering from Cal Poly San Luis Obispo. Our second speaker is Larry Owning, professional engineer, based in Oregon, and he supports the Pacific Northwest, including Oregon, Washington, and Idaho. Prior to joining APA, Larry was General Sales Manager for Louisiana Pacific Corporation, where he managed a team responsible for the sales of all LP products in Western Canada and Northwest United States. Before LP, Larry had 20 years of experience as a commercial construction manager, where he built over 60 significant commercial projects of different types, many of which were primarily wood construction. Larry has a bachelor's and master's degree in civil engineering structures from Washington State University, and he is a registered professional engineer in the state of California. For those of you just joining us, welcome to our webinar, Wall Bracing 5, Wall Bracing Examples in High Seismic Design Categories D0 through D2 regions. I will now turn the microphone over to our first speaker, Alita Dean.
Thank you, Karen. As Karen mentioned, today we're going to be talking about wall bracing in high seismic regions. Our learning objectives today are going to include a basic understanding of wall bracing design procedure and the effect that different design decisions have on the design of your home. And this is all going to be based on the 2018 IRC. These are a couple resources that you might be interested in. The first one is a book titled A Guide to the 2018 IRC Wood Wall Bracing Provisions. This was authored jointly by ICC and APA, and it's available on the iccsafe.org website. Another resource is the publication on the right on your screen titled Introduction to Wall Bracing, and this is a free download that can be found on apawood.org. So the first example that we're going to go through today is straight out of the book on the left. We're going to go through this a bit more in depth, looking at both wind and seismic. After that, we're going to focus just on the seismic design. So the first example, we're going to go through wind and seismic. And since we're focusing on high seismic regions, the latter two examples are going to be on specifically the seismic design. So this is example 4.6 from a guide to the 2018 IRC wood wall bracing provisions. It's a pretty basic two-story home. This is the first floor. And you can see the second floor here. It's got some really large bathrooms. And this is located in seismic design category D2 with a wind exposure B. The seismic design category and wind speed are both mapped out in the IRC, but it's also a good practice when you're starting your design to check with your local jurisdiction. So we're going to start with a preliminary checklist just to make sure that we are qualifying for design with the IRC. And you can see we're definitely meeting the first 4 criteria here. We're a single family home, we're less than 3 stories, and we've got a story height less than 11 foot 7 inches. We're also in seismic design category D2, so we're going to fit in there as well. Since this home is in a high seismic region, we're going to be especially concerned about material weights, which is this last item on the checklist. This is a breakdown of the building weights. Our roof is fairly lightweight, and we're going to be well within that 15 pounds per square foot limit. The floor is sitting right around our 10 PSF or pounds per square foot limit though. Since we're meeting all of our weight limits, we're going to check this last checkbox off of our preliminary checklist. Again, because we're in high seismic, we do have some extra criteria to meet, so we need to check for irregularities. Our exterior walls are all aligned, so we can check off this first one immediately. Since we haven't placed any of our wall bracing yet, we're going to bypass the third item for now and circle back later. So one by one with the remaining checklist items, we do have an overhang at the porch area without lateral support. That's down here at our outer edge. However, it's only 6 feet, which is the absolute largest it can be. So we're going to meet that exception. We're not triggering that irregularity. The largest floor or roof opening is going to be our stair opening. The entire stair footprint is 8 foot by 8 foot. Now, to avoid triggering this irregularity, we are limited to 50% of the least plan dimension. So in this case, our least plan dimension is 25 feet, 50% of which would be 12 foot 6 inches. There's an additional hard limit of 12 feet, which is going to govern. But at 8 foot by 8 foot, we're still well within that limit. So we're going to check off this 4th checkbox. We don't have any floor offsets on this project. That would be a vertical floor offset like you might see in a sunken living room. All of our walls are also orthogonal or perpendicular to each other, so we can check off this second to last one. And we also don't have any concrete or masonry on this project outside of the foundation. In fact, we don't even have a chimney. There are no fireplaces on this project. So we're going to check off that last piece. Now, before laying out our braced wall lines or BWLs, we need to check table R602.10.1.3 for our spacing limitations. The high seismic designation is going to limit our braced wall line spacing to 25 feet. This is a big difference from the 60-foot limit for wind. So if we lay out our braced wall lines like this, we've got just precisely 25 feet between braced wall lines 1 and 2. And the building length in the opposite direction is 38 feet. So that 38 feet is larger even than the exception that we have allowing 35 feet. Therefore, definitely for seismic design, we absolutely need 3 braced wall lines in this direction. Using the same layout at the second floor would look like this. Conveniently, all of the walls stack. Next, let's look at the required length for wind. So we're going to start with wind at the top floor. Now, based on our current layout, we're looking at braced wall line spacing of 25 feet, 24 feet, and 14 feet. So you can see here the 24 feet here, 14 feet here, and the 25 feet here. Now, for the purposes of calculating our required length for wind, we do have the option of ignoring braced wall line B and only using the 25-foot and 38-foot spacing. I'm going to stick with this layout that has a total of 5 braced wall lines, but you do have the option of ignoring this braced wall line for your wind design specifically. So going to table R602.10.3, parentheses 1, you'll note in the upper left corner that the table is set up assuming only 2 braced wall lines. If you check footnote C of this table, it allows us to use the average spacing for the middle braced wall line. So that would give us 14-foot spacing for braced wall line C, 19-foot for braced wall line B, and 24 feet for braced wall line A, and then 25-foot spacing for braced wall lines 1 and 2. Now, using interpolation, we can calculate the following braced length requirements for each of those braced wall lines. Now that you have the base values, we've jotted those down, we need to check for adjustments on table R602.10.3 parentheses 2. So this is a list of the possible triggers for adjustment. I've divided them into green, which applies to all braced wall panel methods, and red, which only applies to select braced wall panel methods. Now this building is exposure B, so we're not triggering the first one unless our eave to ridge height is exactly 10 feet. We're always going to apply the second one. The third adjustment is similar, but we happen to have exactly a 10-foot story height. Now, since we stuck with our 5 total braced wall lines, we are triggering this fourth adjustment factor. We're not anticipating needing extra hold downs at the roof, so we're going to skip that one, and we're planning on gypboard or gypsum board at the interior of all our walls. This floor plan doesn't include a garage, which is normally the wall line I would expect to see this 6th factor applied, because a lot of times the interior of your garages doesn't include gypsum board. For now, we're going to keep this 7th adjustment factor kind of in our back pocket for gypsum board bracing where we don't have quite enough length, but we're not going to trigger it just yet. And then the last adjustment factor is going to come up if you have panel joints in the middle of your wall height. Out here in California, I mostly see wall sheathing installed vertically, so there isn't always horizontal blocking. If you anticipate unblocked edges, you will need to double the amount of brace wall panel length. So this is a pretty hefty increase or adjustment to your wall bracing length. For our building, we're going to come up with the following factors. Note that the 1.3 factor that we have here for having more than 2 braced wall lines is only going to get applied in one direction. So we only have more than 2 braced wall lines in one direction on our building, so we're only going to apply that factor in one direction. I'm also going to pause here and point out that the 1.3 factor could be avoided by ignoring that braced wall line B for our wind design. The dimension between braced wall line A and C is 38 feet, and that's well within the 60-foot maximum dimension for wind. This approach would increase the total required braced wall panel length for wind at the exterior braced wall lines, and the interior braced wall line would only be used for seismic design. So that is still an option. Again, we're sticking with the 5 braced wall line option. If we go back to our calculated lengths and apply the adjustments, we'll get the following minimum required lengths. So this is just the afterwards adjusted values. I stuck these lengths into a table so they're a little bit easier to reference later. I find it's just easier to see and visualize. So now we're going to do the same exact thing, but for the lower floor. We're going to go back to the same table, that's R602.10.3 parentheses 1, and we're going to the next section down. And we're going to, same thing, use interpolation to get base values, which we've got here. And then we're going to go back to the adjustments. The adjustment for the roof height is going to change for the lower floor. So this is a little bit different than the upper floor that we calculated earlier. None of the other adjustments are affected by story, so they're going to be exactly the same. We apply the adjustments by multiplying the base value by both adjustment factors. So with adjustments, we end up with these minimum lengths. Now remember, the numbered brace wall lines don't get the 1.3 adjustment factor, since there are only 2 brace wall lines in that direction. So we're only applying the 1.3 factor to the lettered brace wall lines. For the layout, I like to start with the lowest story because it usually has more open communal spaces and will naturally require the most wall bracing as we try to get that lateral load down into the foundation and out of the house. Sticking these adjusted lengths into a table, we get something like this. I mentioned earlier that we could have ignored braced wall line B for wind. If we had gone that route, just for fun, our lengths would look like this. This approach would add a couple feet to braced wall line A, but it would almost double the length required for braced wall line C. So we're going to eliminate, as we move forward and try to place our braced wall panels, we're going to eliminate the LIB or lead-in bracing method because it's not permitted in seismic design category D2. Just from a cursory look, you can see that braced wall line A has the highest amount of bracing required and the least amount of actual wall length available. So we're going to tackle that one first. We've got 14 feet of wall available. This is going to rule out the gypsum board method because even if we used all of the wall length, we don't have enough length for this method. Otherwise, we're looking pretty good, and we don't actually even need that center braced wall panel. If we look at braced wall line B next, it's apparent that we have plenty of wall length and can similarly use the 2 end portions as braced wall panels. And then braced wall line C is going to look pretty much just like braced wall line A. Now you might think, hey, I only need 6 feet here, and you're right. However, you still need to start and end your braced wall line with a braced wall panel. And each braced wall panel needs to be a minimum width. So if we use the WSP method, we could shorten the 6-foot wall to a 4-foot wall, But practically speaking, your framer is likely going to attach another piece of sheathing next to a window anyways, just to help with the flashing. So that usually looks like this in the field. Going back to our floor plan, we're going to go ahead and place braced wall panels at the ends of braced wall line 1 and braced wall line 2. This is going to easily get us enough wall length. Now going through the wall bracing section checklist, we've got the requirements for panels at each end covered. We've also met our minimum number of panels per line. Braced wall line 1 and 2 both have over 20 feet between braced wall panels though. So to solve this problem, we'll need to stick a braced wall panel midway along each line. And that way we can check off these additional checklist items. Now, our minimum braced wall panel length is based on the method we choose. However, none of our braced wall panels that we just laid out are under 48 inches long. If you check table R602.10.5 for the minimum length, we'll find that for a 9-foot tall wall, we're meeting the minimums for all of the allowable methods. Now, larger widths could be required if you're using CSWSP if the opening height becomes larger than 104 inches. So if you get really large openings while using a continuous sheathing with wood structural panels, you might get slightly larger widths. But otherwise, 48 inches is generally a good rule, especially for intermittent methods. So moving up to our top floor now, I've left the blue lines to show where the brace wall panels we placed below are located. Looking at our required length, we can see that the minimum placement requirements we just checked at the lower story are going to still govern the brace wall panel length at this story. You'll also notice that some of these lines overlap window openings in the story above. So that's in 3 places. We've got circled here. Now, because our goal is to get all of the loads down into the foundations, we're not going to worry about openings in the story above our braced wall panels, but openings in the level below our braced wall panels are a different story. So these won't be a big deal for wind design, but they could trigger a seismic irregularity, so we need to revisit this a little bit later. If we shorten all of the braced wall panels on this floor to a 4-foot or 48-inch length, this is going to be the only location where the braced wall panel at this story occurs over an opening. And we can easily fix this by shifting the braced wall panel over 2 feet to the right, just like that. Now, each lettered braced wall line has a total contributing braced wall panel length of 8 feet. So this is going to satisfy every method except the GB or gypsum board method on braced wall line A. Now, having shifted the braced wall panel in the upper story of braced wall line 1, the wall elevation would look something like this. This offset is the one we're going to keep our eye on when we lay out the seismic bracing. So even though there doesn't appear to be an opening below our braced wall panel, this area in gray here is going to count as open studs. So if it's not constructed like a braced wall panel with sheathing, then it'll count as an opening. Going back to our checklist, we can see we're meeting all of these minimum requirements for braced wall panel spacing and location. And then going back to our irregularity checklist, you'll remember we stuck that one item in our back pocket. If we shift over the lower floor braced wall panel, we can make sure all of our braced wall panels are also stacked. So while some of the upper story braced wall panels are narrower than the braced wall panels below, if we shift that lower braced wall panel at grid line or braced wall line 1 over, we're not going to be overhanging the edges anywhere, and we can check off this last item. If we do that, our overall wind design is going to look like this. So we've got the first floor plan over here and the second floor plan over here. As a comparison, this is what it would look like if we had gone with only 2 braced wall lines in each direction. Now, braced wall line A and C would have each required 11.2 foot of WSP bracing at the lower story and 5.5 feet at the upper story. So this eliminated the interior braced wall line at the upper story without changing the exterior braced wall panels at all. So these look exactly the same whether you incorporated braced wall line B or not. But at the lower story, we ended up shifting that interior wall bracing to the exterior walls. So you have a little bit more bracing at these exterior walls. So now that we've gone through the wind portion, we're going to move on to seismic. Unlike our wind design, the required seismic braced wall panel length is based on braced wall line length and not on braced wall line spacing. The 25-foot spacing is a base assumption of this table. So by limiting the spacing and basing the required bracing on wall line length, we're essentially estimating the tributary floor area for each braced wall line. We're going to start with the top floor. Going to table R602.10.3 parentheses 3. We're going to use 25 feet as the length for our lettered braced wall lines and 38 feet for the length of our numbered braced wall lines. Using interpolation, we're going to come up with the following base length requirements for each of those. And then just like with wind, we're going to need to check for adjustment factors. Seismic adjustments can be found on table R602.10.3 parentheses 4. This is a list of the possible triggers for adjustment in seismic design categories D0 and higher. We're not going to trigger any of these with this project, so we're not going to adjust anything. Now, repeating the procedure for the lower floor, we're going to use the braced wall line length and interpolate to find these base values. Again, notice we moved down in the table for the lower floor. There's a nice graphic here to show which story we're talking about. I put these into a table again. Braced wall line A, again, has the highest amount of overall required length. And the smallest amount of available wall. We've got 14 feet of wall available, as we mentioned before. This is going to rule out that first column. And we're going to definitely need that center braced wall panel this time. If we look at braced wall line B next, we could use all of the available wall and we would just barely exceed the required length for column 1. And then braced wall line C is going to look exactly like braced wall line A. In the other direction, braced wall line 1 has 26 feet of wall available, and that's going to rule out column 1. Only 21 feet is required, so we can shorten these braced wall panels. Braced wall line 2 only has 23.5 feet of wall available. But as we only need 21 feet, we can arrange them a little bit like this. So right now, we've still got lots of braced wall panel method options. We don't need to decide on a method quite yet. Going back to our checklist, we can see we're still meeting all of these minimum requirements for braced wall panel spacing and location. As a side note, this plan has some really nice 4-foot sections of wall at the corners. This isn't always true, so when the wall area at the ends of the braced wall line are shorter, we're kind of forced into a plywood or OSB based method. These methods allow us to locate the first braced wall panel up to 10 feet from the end of the braced wall line, as long as we include 2-foot long return walls on both sides of the corner, or we add a hold down at the nearest braced wall panel end. We'll talk more about this in example 2, but this is an obvious place where the design choice is going to directly affect your hardware costs. So at the upper floor, these are the braced wall panels we had previously placed for wind. At 8 feet total for the lettered braced wall lines and 12-foot total for the numbered braced wall lines, we can stick with this layout for the methods in the last 2 columns on our table. To use a method in the first column, we would need a bit more length. This is going to be impossible at braced wall line A, since the 3-foot section left to us isn't going to meet the minimum length requirements for any of these methods listed in column 1. Braced wall line B, on the other hand, does have plenty of additional wall length available. So we can simply lengthen the upper braced wall panel from 4 feet to 6 feet. And the same can be done at braced wall line C. We need to add a little over 3 feet to braced wall lines 1 and 2, so we'll need to add a whole new braced wall panel to achieve that 15.2 required length. By now we can see that either the braced wall panel minimums or the seismic length is going to govern our design at most, if not all, of the braced wall lines. So I'm going to do a table-to-table comparison just to check that out. This is a comparison of the top floor. So you'll notice I reconfigured the tables a little bit just so they're easier to compare. Between the seismic design tables and the wind design tables, the methods are grouped differently. So I've separated them all out just to visually compare them easier. So on the left, we have the wind values, and on the right are the seismic values. And you're going to notice the seismic is governing for all 5 of the braced wall lines. Then at the lower floor, the same is true. So we're going to move forward with the table on the right, since the seismic lengths are governing over wind. Going back to our irregularity check, we do need to check how those braced wall panels stack up. So the available wall length at braced wall line A ruled out methods in the first column. Methods in the second column are going to look like this. And then methods in the third column would look like this. I've only highlighted here the wall areas that I'm counting as braced wall panels. Obviously, because this orange column is all continuous sheathing methods, the entire wall needs to be sheathed, including above and below the openings and any gable ends. But these would be the qualifying braced wall panels. Notice neither layout includes the braced wall panel overhanging an opening, so we're good on braced wall line A. Now on braced wall line B, we did have the wall area for the methods in the first column, and that would look like this. The methods in the second column would look something like this, and the methods in the third column would look like this. Still no overhanging braced wall panels over an opening, so we're gonna keep on trucking. Braced wall line B is okay. Braced wall line C ruled out methods in the first column at the lower floor. Methods in the second column would look something like this, and the methods in the third column would look like this. Still no braced wall panels overhanging an opening, so braced wall line C gets checked off as well. The available wall length at braced wall line 1, again, ruled out the methods in the first column at the lower floor, but the methods in the second column would look something like this, and methods in the third column would look like this. Again, no braced wall panels overhanging openings, and we're going to check our last braced wall line. So the available wall length on this line also ruled out that first column at the lower floor, and methods in the second column would look like this. Notice we've shifted over this braced wall panel down here to align with the one above. And then methods in the third column would look like this. So we still don't have any braced wall panels at the upper floor overhanging openings at the lower floor, which means we can absolutely check off this last irregularity. We're not triggering it. Now, since we're in high seismic, there are going to be some restrictions on mixing wall bracing methods. Based on our calculations and the lack of a garage, we're not using any alternate braced walls or portal frames. So we don't need to check the last two items. If we stick to intermittent methods, we can take advantage of mixing WSP or wood structural panel method at the exterior and GB or gypsum board method at braced wall line B, which was that interior braced wall line. In plan, that scheme would look something like this, where the blue lines are indicating the wood structural panel method and the green lines indicate the GB or gypsum board method. Now, while the green lines are only shown on one side of the wall here, the gypsum board method needs to be, the gypsum board itself needs to be installed on both sides of the wall for this method. If you only install it on a single side of the wall, that wall length, the contributing wall length needs to be halved. So we're not mixing any intermittent and continuous methods. We can check off this first item, but we are mixing intermittent methods line to line. And that's going to be okay. So that's going to take us through our first example. Again, this is example 4.6 from a guide to the 2018 IRC wood wall bracing provisions. I'm going to move on to example 2, which is not in the book. And again, we're going to specifically from now on focus on the seismic design. So we're not going to go over wind again. This is a modified plan from a major builder in Northern California. This building is a 2-story detached home with a slightly taller story height. Now, being in California, it's also going to be slab on grade, so we're not doing any basements or cripple walls. Going back to that preliminary checklist, we're meeting most of the preliminary checks. Let's take a look at our unit weights for the different building systems or assemblies. This home is going to have asphalt shingles over a layer of OSB roof sheathing. So we've got lightweight plated trusses in the roof and a classic gyp or a gypsum board ceiling below that. All in, we're sitting at around 11 pounds per square foot. Now, if you add in an allowance for a re-roof, we'll be just under our 15 pounds per square foot limit. Obviously, if you want to make this building solar ready, or you're putting solar on the roof, that also needs to get included in this weight takeoff. We're also sticking here with a pretty light floor covering of carpet and some laminate over 23/32 category OSB, and I-joist with a gypsum board ceiling attached to the underside. This assembly is sitting right around the limit of 10 pounds per square foot. Being in California, our exterior walls are mostly covered in stucco, so our wall weight is going to be a bit heavier. So it's still going to be just barely make it under the 15 pounds per square foot limit. So we're going to check off this item. If we look at our irregularity checklist next, just like we did before, noting that all our exterior walls are aligned, we can check off almost all of these. Just like last time, we're going to circle back on the braced wall panel offset in plane, since we haven't placed any of our braced wall panels in plan yet. If we pull out the wall lines that align vertically, we'll get a layout that looks like this. Now, unfortunately, with this layout, the spacing at braced wall lines 1, 2, and 3 exceed 25 feet. The distance between 2 and 3 is to allow for a single room, which would be meeting that exception, but the distance between 1 and 2 are not. So we need to increase our required braced wall panel length. So let's take a look at that penalty. So here you can see we're looking at a 20% increase in required braced wall panel length for braced wall lines 1 through 3 if we stick with this layout. Or we can adjust the floor plan to decrease the spacing. Now, from looking at the plan, we can see that braced wall line 1 has very little wall space available on it. So let's just adjust this floor plan. Here we've moved the master bath and closet to the interior and stacked the walls here on braced wall line 2, with the back of the wall of the garage below. So braced wall line 2 is going to line here with this wall above. Note, this increase in the number of braced wall lines to 4 will increase your required wind bracing by 45% unless we ignore some of these interior braced wall lines for the wind calculation. Again, we're focusing on seismic for the remaining examples, so we're not going to go through wind, but just to keep that in the back of your mind. We're also going to check that there are no cripple walls, which I mentioned before. We're also not putting any stone or masonry veneer on this project. Again, because this is seismic, we are very concerned about weight. So the stone and masonry or any concrete construction outside of the foundation or very isolated locations is going to make a big difference when you talk about seismic design. With this layout, we're looking at a braced wall line length of 23 foot 5 inches for the short direction and 54 foot 8 inches for the long direction. We're going to jump right into the seismic tables. Also going to mention you need to still check wind. We're just skipping that for these last two because this presentation is focusing on high seismic. I've spelled out the interpolation process here just in case you're not used to doing this. So this is the interpolation for each column. We can also interpolate the adjustment factor. So once we've applied the adjustment factor, our required lengths are going to range from 3.8 to 6.8 feet, depending on the bracing method that we decide to use. Remember from the irregularity check that we can only overhang an opening by 1 foot. So That nice 8-foot, 8-inch wall section at the second floor we can't use the entire length. That's right here. That leaves us 2 3-foot sections of wall. That first set of 6 types can be ruled out immediately, since all 6 require a minimum length of 48 inches before the braced wall panel counts towards our total. WSP, or wood structural panel method, can be ruled out for the same reason. We need that 48-inch length. ABW only requires 34 inches and contributes 48 inches to the total. But ABW, or alternate braced wall method, uses a tighter nailing pattern and hold downs to achieve performance comparable to that longer wall section. Now, because of the anchorage requirements, we need to rule out ABW along with the rest of this column. So we're really stuck with continuous sheathing methods on this wall line. Now, in seismic design category D0 through D2, mixing intermittent and continuous methods within a story isn't permitted. So keeping that in mind, we're going to need continuously sheathed braced wall panels at the rest of the second story, now that we've narrowed down our options on this line to only continuous sheathed methods. Let's move down to the ground floor on the same braced wall line, which has even less wall area. So if we follow the same procedure as before, the required total braced wall panel length at this level are shown here. All of these values have been adjusted for our 10-foot, 6-inch story height. Just as before, we can eliminate the types requiring a 48-inch minimum length. The ABW method we discussed above needs 34 inches, so we're going to eliminate that method since we don't quite have 34 inches at this lower floor. Because we're located in seismic design category D0, we're also going to eliminate the PFG method. Our last intermittent method left is PFH. This method only requires 24 inches and it counts as 48 inches. Now, unfortunately, that only gives us 8 feet, and we're looking for over 9 feet of contributing wall length. So unfortunately, all 3 of the remaining continuous sheathed methods are only going to allow us to take the actual length of braced wall panel, and that only amounts to 4 foot 8 inches along this first braced wall line that we're looking at. And that's going to be far less than the 7.88 feet that's required. So our wall itself is around 9 foot tall, giving us a wall aspect ratio over the allowable 3.5 to 1, and that's an IBC limit, or International Building Code. This means we're really forced into a proprietary solution specifically at this wall. Now, if we met that 3.5 to 1 aspect ratio, you could get an engineer to possibly design a shear wall for the equivalent load. Equivalent load is determined here based on the special design provisions for wind and seismic. That's a publication or a standard that's put out by the American Wood Council. 200 pounds per foot is the allowable load for a 3/8 category sheathing, edge nailed at 6 inches on center, as specified for the WSP, or wood structural panel method. So if we took that required 9.24 foot length required for the WSP wall bracing method and multiplied it by 200 pounds per foot, this is one way you might be able to use an engineered solution by designing for this shear load, specifically at this wall. Again, because of our geometry, this specific area is not going to fit within the prescriptive design limitations. but the IRC does allow you to use an engineered solution for portions that do not fit into the IRC. Now moving on to check the rest of our braced wall lines, we're going to get these required braced wall panel lengths. Right now, braced wall line 1 is using CSWSP at the top floor with an engineered or proprietary wall below. Within a story, we are allowed to mix intermittent methods, braced wall line to braced wall line, but again, we're not allowed to mix intermittent methods with continuous methods within a story. So therefore, we need to use a continuous method for the entire top floor because of braced wall line 1. Unfortunately, this wall line, we're looking at braced wall line 2 now. But unfortunately, this braced wall line doesn't have braced wall panels at both ends. You'll notice we're not very wide out here, so we're missing a braced wall panel at this end. We also don't have those 24-inch return walls. We've only got a foot of length at that end. So this means that we're going to need to put an 1,800-pound hold down at the end. At the upper story, this might look like a strap instead of a traditional hold down. We can see that we have far more than the 3.79 feet required for that upper story. Because of the geometry, we're still stuck with 2 walls. In theory, you could reduce the braced wall panel widths at each panel. But since we're using a continuous sheathed method, it's not really going to make a difference in the final construction. On the bottom story, we are still able to use intermittent sheathing. As a side note, it's pretty rare to use an intermittent method on the bottom when the upper story is continuously sheathed. But that's just a side note. If we stick with WSP or wood structural panel method, we can still use the end conditions available to the continuous sheathed methods. So this story also has available wall area almost twice the length required, and could be pared down to 2 smaller walls. Braced wall line 3 also doesn't have braced wall panels at both ends, but it's okay because we're using CSWSP method at the upper floor. We also don't have those 24-inch return walls at the end of the braced wall line, so we're going to have hold downs again. You might notice the orange area at the top floor is over a door opening. Now, because this opening is less than 4 feet, we can use the full length as long as the header is at least a 2x12 or a double 2x10. In theory, we only need this much wall. From our discussion of braced wall line 1, we also know that the 3-foot 3-inch braced wall panel on the ground floor would need to be an ABW, since we're not meeting that 48-inch minimum width for WSP method. If we did that, this would mean hold downs at either end of that wall. If we reduce the wall layout to our minimum length required, it would look like this. Because we again do not have braced wall panels at the right hand end of the wall, nor those 2-foot return walls, we need to add hold downs at the end of the first braced wall panel. Braced wall line 4 doesn't have braced wall panels at both ends, but it does have those 24-inch return walls at the end of the braced wall line, so we're not going to need hold downs at this braced wall line. Notice on the top floor, we're not using the full 8 foot 2 inches of wall length at this wall. If you recall the irregularity check we did earlier, braced wall panels above can overhang the opening by up to a foot without issue. We theoretically could use even more of the length with the right header, but as it is, we have plenty of length, so it's really not necessary. You might also think, hey, I have way more wall length at the top floor than I need. Can I reduce it? And again, the answer is yes. Probably not in reality by very much. In order to keep a braced wall panel within 10 feet of the end of the braced wall line, we are forced to have at least 2 panels. If you really wanted to get stingy, you could make both braced wall panels exactly 4 feet long. However, again, your framer is likely going to be adding most of that sheathing back in around the opening to attach the window flashing. So before you go through the extra effort of reducing everything to the bare minimums, just think about what you're really saving and what the installer is going to put in. Because I've definitely run across this type of situation a lot. Now, this is an engineered example, but I'm going to point out here a common constructability detail at the window openings. So you can kind of understand the panel on the right. It appears to be right around 4 feet, so you've got that standard panel width and a couple more feet before we hit the sheathing around the opening. But the panel on the left runs right into the sheathing at the opening. Now, from the strap location you see here, you can see where the panel that they're counting is actually ending. So here we're providing an extra foot of sheathing, but we're not getting any credit for it. And this is one of those cases where I think we want full credit for the sheathing we're providing. So just think about, what you're really saving by only counting a slightly narrower or slightly shorter wall length. I'm going to move on now to check braced wall lines A and B. You'll notice that the braced wall line lengths in the table only go up to 50 feet. So braced wall line A and B are over 50 feet, which brings us to footnote C. Footnote C directs us to split the line into shorter segments. Note that each of these segments needs to comply with the table individually. So this is a little extra insurance that our braced wall panels are distributed according to where the load is, according to that tributary load. So you can't stack all of your braced wall panels on one end of your braced wall line. At this point, we've worked through all the shorter braced wall lines, and we're moving on to our longer braced wall lines A and B. And you can see the available first pass at our WSP panels available. We've added 2-foot return walls at braced wall line 2, and this is to avoid the hold downs on that braced wall line 2. So when you add those 24-inch return walls, they need to be in 2 orthogonal directions. They can't just be in one orthogonal direction. Now, also remember this line is longer than 50 feet, so we split up the line length to find our required braced wall panel length in the table. Now on this side of the building, our exterior wall jogs at braced wall line 3. And so that's where I've decided to split it. This gave us a braced wall line length of 29 foot 8 inches, which I'm just going to call 30 feet to the right, and 25 feet to the left. Using the table, that's going to give us a 4.6 foot and a 3.85 foot required length, respectively. After applying our adjustment factor of 1.05, that's going to give us a total required length that's shown in this table. Because our minimum qualifying wall length for CSWSP is only 27 inches for openings shorter than 6 feet, we're easily going to meet our required length at this story. Our 7-foot 6-inch wall is just barely within that 20 feet. So we're just barely getting 20 feet in between here. So we do definitely need to keep that 7-foot 6-inch wall. Unfortunately, the 7-foot 6-inch wall isn't within 10 feet of this end. So we do need another wall in between. Again, you could reduce these panel lengths, but since we're continuously sheathing, we're going to end up with about the same cost from a material standpoint. The lower story might be a little bit more worthwhile of an exercise. So if we reduce that, that would look like this and saves us about 9.5 feet of panel length. Last wall line, hopefully we've got some steam going and we can spot issues and opportunities a little bit faster. Right away, we can see there's not a return wall on the ground floor at braced wall line 4. So let's add a hold down. We easily made the 4.83 foot requirement between braced wall lines 1 and 3. We're missing a braced wall panel within 10 feet of the left end though. So let's add the full length of this end panel. And this is a lot of available wall length. We could definitely reduce this. So first, let's remove that 7-foot 1-inch wall. We're still well within 20 feet of the next braced wall panel. Second, we only need 4.7 feet between braced wall lines 3 and 4, not 10 feet. We're going to reduce that. And at the ground floor, we need 9.9 feet in this section. So we're going to reduce that, and 11.9 feet to the right of braced wall line 3. So we can cut that down a little bit. In plan, our solution would then look like this. Again, we ended up with 2 proprietary or engineered piers up at the top here. And we ended up with a total of 3 hold downs shown here at these locations, and 2 straps, which we're going to put over here at the upper story. And that really takes us through example 2. I'm going to check in.
Hey, Alita, it's Karen.
Hi, Karen.
Excellent work on those first 2 examples. Larry, our second presenter, he is online, so if you can release the screen.
All right, bear with us while we transfer.
We are viewing your screen, Larry, so we'll go ahead and turn the mic over to you now.
So thanks, Karen, and thanks, Alita, and hello, everyone. Let me begin my portion of the presentation by working through a townhouse example. This is a plan from a builder in the Pacific Northwest. This building is a 2-story townhome with 9-foot tall first floor walls and 8-foot tall second floor walls. Note the story heights are 10.5 feet for the first story and 9.5 feet for the second story. For brevity, I'm going to present this as a slab-on-grade structure, even though this project was built as a raised floor sitting on continuous foundations. Or if you're like me from the Pacific Northwest, we call this crawl space construction. During this example, we'll highlight the more important steps in establishing our braced wall panels. This plan was repeated 4 times in a row to make the building a 4-plex. We're going to just focus on one of the end units. We'll start off with our preliminary checklist. We're meeting most of the preliminary checks. Let's look at our unit weights for the different building systems. First, let's look at the weight of our roof and ceiling structure. this townhouse project is going to be built with concrete tile roofing over 7/16 OSB sheathing. The roof structure is lightweight prefabricated roof trusses at 24 inches on center with a single layer of drywall for the second floor ceiling. All in, we're around 17 pounds per square foot for the roof ceiling assembly, which is just above the 15 pounds per square foot base code limit. Fortunately, the code allows the roof ceiling assembly to exceed 15 pounds per square foot if we use an adjustment factor from table R 602.10.3 Applying this adjustment factor will allow us to go up to 25 pounds per square foot. We're sticking with a pretty light floor system. They'll use carpet and some laminate flooring over 23 32nd OSB sheathing over I-joists at 16 inches on center. They'll use a single layer of drywall for the first floor ceiling. This floor assembly weight is right at the prescriptive floor dead load limit of 10 pounds per square foot. Let's look at table R 602.10.3 for the adjustment factor for our roof ceiling assembly since it's greater than 15 pounds per square foot. Looking at the table, we have an adjustment factor of 1.1 for the first floor and an adjustment factor of 1.2 for the second floor. Note that any top story would get the 1.2 factor. You might think of the 1.1 and 1.2 factors as a 10% and 20% adder for the extra roof ceiling weight of 17 pounds per square foot. The reason the top story gets a higher factor of 1.2 rather than 1.1 is due to the proximity of the roof ceiling mass associated with the top story. Now let's look at our plan configuration. If we look at our irregularity checklist, our exterior walls are stacked, but not all of the interior walls are stacked. From our previous examples, we know that we're going to need at least one interior horizontal braced wall line to meet our seismic spacing requirements. For now, let's put the braced wall line spacing topic on hold and check the rest of the list. We do have a small porch overhang area at the front entrance. The overhang is only 4 feet deep, so it's not going to qualify as an irregularity. We can check the last 4 items in the checklist as good to go. We'll circle back on the first bullet, which is checking our interior braced wall panels to make sure any offsets are not out of plane after we've located our braced wall lines. Here's an obvious first take on laying out the braced wall lines. Using this layout and with attention to where we place the braced wall panels, we can comply with the irregularity checklist for the interior braced wall offsets. Unfortunately, with this layout, the spacing between braced wall lines 2 and 3 exceeds 25-foot spacing. For this layout to work, we're going to have to use the second exception listed in the slide and use an adjustment factor from the seismic adjustment table R 602.10.3 After looking at the table, we find that we'll be applying a 20% increase in required braced wall panel length for both braced wall lines 2 and 3 if we stick with this layout. Or, if you're not happy using a 20% adjustment factor, you could redesign the floor plan to add another interior braced wall line. Sticking with our initial braced wall line layout, we determined that the braced wall lengths for lines 1, 2, and 3 are 23 feet, and the length for braced wall lines A and B are 60 feet. Starting with the top floor of the townhouse and going to table R 602.10.3 we're going to use 23 feet as the length for our numbered braced wall lines and 60 feet for our lettered braced wall lines. Using interpolation, we calculate the base length requirements as shown on the slide. Using footnote C of the table, we split the 60-foot dimension into 2 segments of 30 feet, and therefore we multiply the 30-foot table values by 2 to obtain the required braced wall panel lengths of 24, 24, 15, and 12.8 feet as shown by the green rectangle in the slide. Sticking with the top floor, the next step is to apply our seismic adjustment from table R602.10.3 parentheses 4 to the total required length of wall bracing we determined in the last slide. Specifically, we're going to apply the braced wall line spacing and the roof dead load adjustments. The wall line spacing adjustment of 1.4 is going to apply at braced wall lines 2 and 3, which are 35 feet apart. When we apply the weight and spacing adjustments, all the required braced wall lengths will get the top floor weight adjustment of 1.2, but only the middle row in the slide above is getting the braced wall line spacing adjustment of 1.4. After adjustment factors are applied, we establish the required total length of braced wall needed for our project. Let's repeat the process of analyzing the required length of braced wall panels for the lower floor of the townhome. Again, using footnote C, we get these base values from table R602.10.3 parentheses 3 for our required lengths. Since we have a 10.5 foot first story height, we're going to add a small story height adjustment of 1.05. And we're dropping the roof dead load adjustment down to 1.1. We still have the 1.4 braced wall line spacing adjustment for braced wall lines 2 and 3. When we apply the adjustment factors for the bottom floor to the values from table R602.10.3 parentheses 3, one of the calculated lengths for the braced wall lines 2 and 3 is 28 feet. Which is actually longer than our braced wall line length of 23 feet. So the braced wall line methods in this column are definitely not going to work. Looking at the length of wall available for bracing at braced wall line 1, we can see we have 2 garage walls of 3 foot 6 inches or 7 feet of total wall. Reviewing our adjusted required bracing length values of 20 feet, 14.7 feet and 12.5 feet for braced wall line 1 in the table, it's apparent that 7 feet of actual wall is not enough, and because of that, we're going to need an engineered solution at the first floor braced wall line 1. So let's summarize our required braced wall panel lengths by floor in the table on the right. We have a decent amount of wall we can use for braced wall panels at the upper floor. Our wall piers at each end of the braced wall line are shorter than 48 inches. So we're going to rule out this first column of intermittent methods as well as WSP. Because we're on the second floor, we're ruling out ABW and PFH because of their anchorage requirements. I'm also going to eliminate CSG since this isn't a ground level garage. This leaves us with method CS-WSP. This method allows us to count all the full height wall segments, but to avoid any of the irregularities we checked earlier, we're only going to count the end wall piers. CS-WSP method calculates the minimum braced wall length based on the wall height and adjacent opening height. So let's look at table R602.10.5 to double check that we're meeting the required minimum of 5.91 feet of braced wall panel. Continuing with the upper floor, because our actual braced wall panel width is 3 foot 6 inches, which is less than 48 inches, we need to look at table R602.10.5, and based upon the adjacent opening height, we're going to determine the contributing length of braced wall panel we can get credit for. Verifying the contributing length is an important step to do anytime you have openings next to CS-WSP panels. For our example, because the upper floor height is 8 feet, we're looking at the 8-foot wall height column in the table. Let's take a second to look at something interesting about this table. You'll notice that as we approach the 96 inches or 8-foot clear opening height, we get to that 48-inch minimum width required for CS-WSP. But for other wall heights, we're going to need larger widths. This is ensuring a minimum 2-to-1 wall aspect ratio for all the wall piers that we're counting. So now back to looking at our wall elevation. Let's assume our window opening heights are 48 inches for the opening on the left and 68 inches for the opening on the right. From the table, we need 24 inches and 26 inches for our minimum wall length. Remember, both of our end panels are 3 foot 6 inches or 42 inches long and stacked with the walls below. So since we exceed the minimum required length in the wall height columns, we can use the actual width for the contributing braced wall length. So in our case, that's a total of 84 inches or 7 feet for the two panels, which exceeds the previously calculated required braced length of 5.91 feet. Therefore, we have met the prescriptive code required wall bracing length on this upper floor wall line. Remember that since we are using continuous sheathing methods at this upper story, the entire story will need to be continuously sheathed. In high seismic regions, we are not allowed to mix intermittent methods and continuous sheathing methods within a story. We can, however, mix intermittent methods and continuous sheathing methods story to story. So just because our top floor is using continuous sheathing doesn't mean our bottom floor has to be continuous. We're going to calculate the equivalent load for the lower floor by pulling from the WSP column as shown on the table. Remember that we've already determined that the lower floor braced wall line at the garage will not meet prescriptive design. This townhome then becomes a perfect example of a hybrid approach where most of the walls can be designed prescriptively, but a few may need to be engineered. Perhaps you remember from Alita's portion of the presentation where she said if we meet the 3.5-to-1 aspect ratio for the wall, an engineer could possibly design a shear wall for the equivalent load. Let me remind you that the equivalent load is determined based on the special design provisions for wind and seismic publication, which is by ANSI and the AWC. From that publication, 200 pounds per lineal foot is the allowable load for 3/8 category sheathing edge nailed at 6 inches on center. Using the WSP value of 14.7 from the table and multiplying that value by 200 pounds per lineal foot gives us 2,940 pounds of lateral load we need to design for at the garage wall line. You can also think of the 2,940 pounds as 1,470 pounds per each garage wall pier. The engineer can design for the 2,940 pounds of total lateral load in various ways. Discussing those various ways in the engineering designs is beyond the scope of this presentation. Moving on to braced wall line 2 at the upper floor, I've crossed out the WSP column to remind us that we only get to use continuous methods on this story. Because this is an upper story, that really means CSWSP. We have a lot of wall area along this line, and all these walls are meeting that 2-to-1 aspect ratio we noted on the minimum length table. We're definitely able to meet the 8.29 feet of required braced wall length on this wall line. At the lower floor, we have a total of 20.25 feet of available wall length. Unfortunately, we need 20.6 feet for intermittent method. This is where you can see those adjustment factors really force us into using continuous sheathing methods without adjusting either the story height, rate, roof weight, or braced wall line spacing. And because we can't mix intermittent and continuously sheathed methods within a story, we're stuck with the CSWSP method at the entire lower story. From the table, using CSWSP, we need 17.5 feet, which is no problem since we have 20.25 feet of available braced wall length. For brevity, we'll skip the braced wall line 3 and focus on our long walls, braced wall lines A and B. We know that At all the party walls, they're all going to be solid with no openings, but the end units have window openings as shown in this slide. Let's concentrate on these walls. There is naturally a lot of wall area for bracing since these type of townhomes are usually built on narrow lots. In a similar manner to the previous slides, in the table shown, we established that the braced wall panel lengths were required. You can see there's plenty of opportunity to provide 32.3 feet of braced wall on the first floor and 15.4 feet of braced wall on the second floor. A prescriptive approach works very easily for these walls. Note, we were able to avoid concerns about irregularities by placing our highlighted braced wall panels away from where the windows stack over each other. We'll consider braced wall lines A and B as good using prescriptive code. This slide shows our wall bracing solutions by highlighting our braced wall panels in orangish colored lines. We were able to use prescriptive wall bracing everywhere except at the first story braced wall lines 1 and 3. Both of these wall lines require engineering. In summary, we were able to apply prescriptive solutions rather quickly and identify any areas which required engineering. The wall bracing solutions we show above could definitely be called a hybrid wall bracing design. Now let's move on to our next wall bracing topic, which looks at how you might design additions. We get asked quite a bit, how do you analyze and design wall bracing for home additions using residential prescriptive wall bracing? In the next few slides, let me present a non-inclusive list of ideas on how you might use prescriptive wall bracing for additions. Note that I'm not going to go through designing the wall bracing in detail because we've done that in the previous 3 examples. Rather, I'm just going to introduce a few ideas which might allow the use of prescriptive code. Before we get too deep into your additions wall bracing design, look at the overall plan configuration and consider if the structure will qualify for prescriptive design. Check for things like irregularities, plan geometry, story-to-story stacking, wall heights, dead loads, concrete or masonry construction, etc. If some walls don't qualify for prescriptive, maybe you design the addition as a hybrid where some but not all the walls might need engineering. If none of the walls or structure qualify prescriptively, you'll be required to use engineering for all your wall bracing. Here's one of the previously used checklists, which is a great resource to begin assessing if the addition will qualify for prescriptive design. We used this same list in the previous examples. Another great place to start is checking the addition is to see if it passes the irregularity checklist. Remember the irregularity flowchart from our module 4. If your existing home has an irregularity, but the addition passes the irregularity checklist, you'll want to verify with the local jurisdiction that they will accept prescriptive wall bracing for the new addition. If the irregularity of the existing home doesn't affect the addition might be acceptable to be designed prescriptively. Any shared braced wall lines between the addition and existing structure would require more rigorous design analysis. Here's a full slide view of the irregularity flowchart shown in the last slide and presented in our last webinar, Wall Bracing 4, Wall Bracing in High Seismic Regions. Again, this flowchart is a great resource for systematic review of both the existing and new addition structures for any irregularities which might cause you to use engineering over prescriptive design. Here's some more code compliance checks. Regarding the first bullet, you may have an existing home that was originally designed with intermittent methods, and you want to utilize continuous sheathing methods for the addition. Remember that current code for new homes will not allow the mixing of intermittent and continuous sheathing methods within a braced wall line or story. You also cannot mix intermittent methods within a braced wall line. That said, if you're adding continuous sheathing methods to an existing intermittent method wall line, the local building code official might find that increasing the bracing method to continuous sheathing is acceptable. The rest of the list in this slide is self-explanatory, and we've previously reviewed them. So you've done a preliminary check, and you've done any preliminary local code reviews, and you've found out that you're ensuring compliance. So now what? Let's run through some possible ideas of using the residential code to calculate the required braced wall panels on home additions. Let's begin by combining the addition with the existing house and designing the wall bracing for the whole structure. Specifically account for the braced wall requirements at any shared walls. Create braced wall lines which include the whole structure, both existing and new. This method could be a challenge as you would need to know the existing structure construction and the existing wall bracing design. Let's look at another possibility. You might need to engineer the shared walls between new and existing structures and then use prescriptive wall bracing design on the remainder of the addition. Again, the challenge will be knowing the design and construction of any shared walls, including their footing design and capacity. Let's keep going with more ideas. The third idea is like the last one, except at the shared wall. In this idea, you would prescriptively design all the sides of the new addition as if it is a separate building and add the calculated wall bracing lengths to any shared walls of the existing building. For example, if you prescriptively calculated that the shared wall of the new addition needed 10 foot of braced wall panel, you would need to add that 10-foot bracing length to the existing wall. Again, this could be a challenge as you would need to know the existing bracing design in order to verify that the shared wall would have the extra capacity to handle the added bracing length from the prescriptive design. Our next idea breaks this concept down. This idea is methodically expanding upon the last. Maybe your addition to existing structure can be thought of as a T or an L-shaped building. Let's break down the design concept for a T or L-shaped building step by step. Step one is dividing the structure into two rectangular elements. Step two is to determine the bracing requirements for each rectangular element. Step three is rejoining the rectangles and following 5 design guidelines. Here's the rules for rejoining our rectangles. The common side must account for the bracing required in rectangle 1 and rectangle 2. You can utilize the entire shared wall line and not necessarily just where the wall intersects. An example of not using the shared wall might be the use of a collector across that shared length. To do this, you'll have to make sure you meet code provisions for braced wall panels at the end of braced wall lines while using a collector. As we mentioned before, watch that you're not mixing methods within a story or braced wall line. If you're using intermittent methods, the length of required bracing shall be the highest of the intermittent methods used. Also, you would need to use the highest amount of bracing required from both a wind and a seismic design analysis. In this example, if you don't have a common wall, you might look to include all the required bracing at the exterior extension of the common wall. We've discussed just 4 possibilities on how you might use prescriptive wall bracing for an addition. These certainly could be more possibilities than what I just discussed. Whatever method you use, check both wind and seismic and make sure you use the most conservative result. The APA wall bracing calculator can be a great tool to use as it allows you to look at each wall separately for prescriptive compliance. The calculator also checks for both wind and seismic simultaneously. Note that the APA wall bracing calculator does not check for irregularities or story-to-story requirements. These checks will need to be done prior to use of the calculator. One of the biggest watchouts is accounting for the actual existing foundation construction and making sure it has the capacity for any additional lateral and gravity loads. Let's look back and summarize today's learning objectives. We wanted to run through some actual plans to show you the basic procedures for prescriptive design. During the examples, we saw that various design choices could influence the use of residential building code. We looked at hybrid approaches to designing wall bracing where maybe a few portions of the building needed engineering, but the majority could be designed prescriptively. And lastly, we discussed some possible ideas on how one might go about using prescriptive wall bracing on additions. Before I turn the controls back to our moderator, Karen, I want to make sure you're aware of a few APA wall bracing resources. As we mentioned during the last section here on additions, APA has a wall bracing calculator available on our website. The calculator is updated for every code cycle beginning with the 2009 IRC and is currently updated through the 2018 IRC. There is a downloadable quick start guide and a short step-by-step video available at our APA wall bracing webpage. There's a couple of great wall bracing resources that you may be interested in. On the left is a book for purchase titled A Guide to the 2018 IRC Wood Wall Bracing Provisions, which was co-authored by the ICC and APA. Another resource on the right is a free APA publication called Introduction to Wall Bracing. Both of these publications can be accessed through APA's wall bracing webpage. So at this time, I'll turn the controls back over to our moderator, Karen, who will finish up today's presentation.
Thank you so much, Larry, and thank you, Alita. I'm looking at the clock, and we absolutely don't have any time for a live Q&A. So thank you for those of you who did submit questions. We answered almost all of them during the session. You can follow up with us for some more. I would note that that QR code has reappeared, so please do take a moment. Give us your feedback on today's session. What could be better? What would you like to see in the future? That's super valuable to us. And as mentioned, if we didn't get to your questions, we will share those with our field services team, and we'll get back to you as soon as we can on those. I want to just touch on the last few of those housekeeping reminders. Please don't forget to download your AIA or ICC certificate of completion, and make sure that you're signed up to receive our APA update newsletter so that you'll be notified of our future webinars as well as updates to our APA publications and standards. To receive it, all you need to do is from our homepage, click on Sign In the upper right-hand corner of the page. In the drop-down menu, you will select Register, and then you need to let us know what you'd like to receive. In this case, it would be the APA update newsletter. Lastly, we have field staff located throughout the country. These talented people like Alita and Larry are available to assist design professionals, builders, and code officials. Their individual contact information can be found on our APA website, apawood.org. Please reach out and take advantage of this free resource. And with that, I'd like to thank you all for attending. Have a great day.